Okay, good. So yesterday we talked about iconal scattering of a high energy particle of a classical color field. I also said a few words about iconal vertex, which is kind of what you can use to do the same kinematical approximation in an actual Feynman diagram calculation. I'm not going to have a lot of I'm not going to be reviewing experimental data, but I have one data plot or one slide with two plots to motivate a little bit what kind of experimental observables that the calculation we're going to do today could be relevant for. So this is something that is known as RPA. So who has heard of RPA? Other people have not heard of. This is heavy ion jargon. So RPA. Okay, so this is what is RPA? RPA is a nuclear modification ratio. So it is a cross section in a proton nucleus collision divided by A times the cross section in a proton collision. And in this case, so in principle, you could define such a ratio. But anyway, so this is the idea is that, okay, your proton nucleus versus proton nucleus is different from a proton. This is kind of a convenient way to parameterize how nuclei are different from protons in a way that cancels out a lot of systematical and experimental uncertainties. Fragmentation. There's a lot of things that cancel out, and somehow the idea is that this would help you focus on things that how are nuclei different from protons. And of course, for us, if we're thinking about saturation, one of the reasons we expect nuclei to be different is that gluon saturation effect should be more important in nuclei. There's more more color in nuclei, so we would expect gluon saturation to be more important. These particular plots are RPA for single inclusive charged hadrons from charged particles. Yeah. So all charged hadrons measured by Alice and LHCb. So all charged hadrons to first approximation are pi plus and pi minus. Okay, most of the if you're not somehow more specific, you don't try to identify them. Why charge? Because charge are easier to see than neutral. You can measure neutral, but it's a little bit more tricky. So high zeros you can measure, but charge are easy to measure. There's a magnetic field in your detector. You see the tracks, and charged particles see the track. Then identifying the particles is a bit more difficult. So okay, so this is a nuclear modification ratio. So this is Alice. Non-single diffractive events, proton nucleus collisions at 5.02, eta CMS less than 0.3. Yesterday we talked about the rapidity. So this eta is a pseudo rapidity. It's almost rapidity, not exactly rapidity, but for our purposes here, we can think of it as rapidity because it's a eta equals 0 or close to 0. So this is a proton nucleus collision almost in the center of mass frame. The LHC beams are a little bit boosted. The proton beam has a little bit higher energy than the nuclear beam, so it's a little bit off center, but it's close to mid-rapidity. So it's close to this kind of a 90-degree angle configuration. So here is the RPA, of course, kind of normalized in such a way that A is the mass number, right? Normalized in such a way that somehow if there are no nuclear effects, this would be 1. Then there's a couple of calculations. So this is a panel from a larger plot that has other calculations than CGC calculations. Also, I just do the one which has the CGC calculations. I think I was involved in the orange one. Then somebody. Okay. We would have to check which one. So these are kind of different versions of gluon saturation calculations with a little bit differences here and there. There's experimental data points which have statistical error. Then there's also an overall luminosity uncertainty because so there's a correlated error which shifts all the points up and down at the same time, and then there are point-to-point statistical errors that make them fluctuate a little. So it's a bit curious that it doesn't seem to go to 1, but it seems to go to 1.1 at large PT. So this is, sorry, I also clicked out the axis. This is translate mode axis.
What's the right hand side? What's the value? What are the values for PT?
Oh, I don't know. I think this, so this is at least, this must be go up to around 10 GB.
10 GB.
Around, if I remember, you have to, you'd have to look from the for the reference. I don't think I have a link here. Yeah. So this is not just charged particles. I think you start running out of statistics. This is the older first proton led run, so you don't have. At some point, you run out of statistics for charged particles and time. I think that we're talking about. I think this is 1, 2, 3, 4, 5, 6, 7. Probably, we have to check. So anyway, kind of the interesting stuff from my point of view is happening here, right? And we're talking the kind of the 1, 2, 3 GB. 1, 2, 3 GB region where kind of things that are not flat anymore, but they go down. And so in some sense, well, we're not gonna get all the way there to this lecture, but somehow. And so I can try to give you some ingredients of how you could understand why things start to happen here quite somehow dramatically when you go to low peak. This is a similar plot from the LHCb. Now this is forward rapidity. So this is kind of in the proton going direction. Right? The same observable, but looking in the proton going direction at forward angle. Again, there's a calculation with the collinear factorization. And there's some other calculation which is I think not visible here. That's because that's a calculation for backward rapidity. So I clip out something. Oh, and I seem to have clipped out the PTs again here. I can make a better version with the scale. Anyway, we're talking about 1, 2, 3, 1, 2, 3, 4, 5. I think this probably goes on to 3 or 5, 4 or 5 G. Okay, so kind of see a similar thing. The data points kind of at high PT, they're kind of close to 1. Then they go down, and then maybe you want to try to understand how they go down. So this is a little bit of a kind of an additional thing here, is that kind of here you have something that is differential in eta. So you would of course like to understand both how things change as a function of PT, and you would like to understand how things change as a function of eta, because what you see is that when you go to more and more forward, you can somehow the effect is bigger and bigger. And if you squint, you can see that these are gradually, not very rapidly, but gradually going. The points are going down when you go to forward. When you go to more forward rapidities. So I think the general feature of why you go down as a function of PT we can understand quite easily, and that is kind of the first order, in some sense, a first order effect of saturation. In order to understand what happens in rapidity, we would really like to understand QCD evolution. So GMOC BK evolution tells you how cross sections change as a function of rapidity. So in principle, what we would, this is the kind of thing that BK evolution should be able to understand. And of course, here the problem is a little bit, we discussed yesterday about this asymptotic energy. This is about as forward as you can go at the LHC. The square root finite collision energy is finite, and somehow this evolution, the way we understand it in QCD, it goes like alpha s. It goes with alpha s times the rapidity. Kind of, and alpha s is small enough. So the kind of things that we are trying to understand vary relatively slowly with rapidity, and there's always the question of do you have a collision energy that is high enough that you could really unambiguously see signals of BK evolution in experimental data. Always gets a little bit sometimes difficult. But these are the kind of things that we would like to be able to understand. Okay. Yeah.
You say you said that the lower bound for what is considered DIS interaction involves an energy scale of about 100 GeV.
Oh, energy, but that's beam energy, right?
That's the center of mass.
That's the center of mass. So here we are talking about LH. So the beam energy is 5 GeV. 5,000 GeV. So we're certainly high enough energy. So typically, when you start talking about small x physics, when your beam energy is 100 GeV or higher, and then you're looking at transverse momenta of the order of 123 GeV, and we are very much in this region. Our beam energy is 5,000 GeV.
Is there an upper bound of what kind of GIS collisions we can actually do with current colliders?
Yes, there's always there are currently no DIS colliders. So this is LHC. This is not DIS. It goes to higher energy. The highest energy DIS so far was Hera, which is shut down already. And Hera went to an S of about 300 GeV, the collision energy. Collision square root S of about 300 GeV. The new DIS collider EIC, which is kind of will start construction in a couple of years, will be at lower center of mass energy. Problem there, of course, is that higher energy costs more money. These are expensive instruments, especially for electron beams going to high energy is very difficult. This is why LHC is protons and nuclei, and you can more easily go to higher energies with protons and nuclei than you can with electrons because of synchrotron radiation. So that's a topic for another discussion. We could talk about beam energies and costs. There's fascinating things there too.
This EIC is probably not much chance in that direction.
Well, EIC is kind of on the limit because what you lose in square root S, you gain in the fact that you have nuclei, which you did not at Hera. And nuclei, so there are pros and cons. There are nuclei, you have a better program of exclusive reactions. You have much more luminosity, you can do exclusive reactions better. But again, so I would say that you go into the saturation regime, you go to small, and you go to x equals 10 to the minus 3 at the EIC. What you don't see is kind of asymptotic. I mean, you don't get into asymptotically small x. So you see some aspects of saturation, but not the kind of aspects of actually resumming alpha is log 1 over x. And this resummation for alpha is log of 1 over x to be really large and require resummation, and this resummation to give you something very non-trivial that would require much higher energies. But then there are other aspects of saturation that you can see. Good. So that was kind of as a motivation for experimental from experimental data. A little bit right on. Experimental data. So before we go into the calculation of how one would calculate these kind of things, let's look a little bit at kinematics. So I said that we want to be at small x. So let's just take a little bit of a closer look on the kinematics, in particular the kinematics of this kind of an LHCP-like forward rapidity process. So we start from having a proton. Okay, and then we have a nucleus. Okay, and I'm going to say that the proton has a p plus, and the nucleus has a p minus. So the proton is going in the positive direction, nucleus is going in the negative direction. Okay, and then we are going to produce something here. So there, proton is going that way, nucleus is going that way, and we're going to produce a particle. We're going to produce a particle with a transverse momentum and a rapidity, and we're going to produce a particle with a rapidity greater than 0. So my convention is that here, at least in this case, tomorrow we're actually going to change directions. But so this is in the proton going direction. Okay. So you remember the mass on shell relation. If the proton has a large, P plus. Okay, so first let's calculate the center of mass energy. So let's be in the center of mass system. Except that now the convention, I will follow the usual convention, which is kind of sounds weird if you first hear it, but it's actually more convenient for scale or working with nuclei, which is that I will look at the proton nucleon center of mass system. So I will somehow be in a system where boost to a Lorentz frame where the energy of this proton is the same as the energy of one of the nucleons in this nucleus, right? So I'm not going to be in the proton nucleus center of mass where I'm going to be in the proton nucleon center of mass system, which means that overall the nucleus has much more energy, but each, of course, because the energy of the nucleus is the sum of the energies of the nucleons, I'm going to be in a system where every nucleon has the same energy, but opposite direction momentum as the proton. So I'm going to be in a system where P plus of the proton is the same as P minus of the nucleus divided by the mass. So that's the energy per nucleon. And this is not exactly the frame at which the LHC is sitting, but it's not far. Okay, so and I'm going to measure a particle here which has some transverse momentum, and it is going at forward rapidity. So what's the kinematics of this particle? This particle has some K plus momentum, which, if I go back to my formulas, the K plus momentum that this particle has is K per times exponential of rapidity. And I will write this as I want to scale out a factor of the proton P plus. So I write this as K per exponential of rapidity time over P plus times P plus. So yeah, I didn't do anything. I just divided and multiplied by P plus. And then the same thing I will do for the K minus of this particle, which is 1 over square root 2 K per exponential of minus y. And in this case, I will of course scale out with exponential of minus y over P minus over A and P minus over A, right? The energy of the oligo. Okay. So now here, the essential argument is that because I have a proton here, and so these are equal to square root S divided by 2, and square root S is the collision energy, which is 5 TeV. So this is big. Okay. So if I look at the mass shell relations, P minus of the proton is the proton mass squared over 2 P plus. Proton mass is 1 GeV. This is 1 GeV squared divided by square root S, which is 5 TeV, right? So this is very, very small, right? So the proton is going to the right. It only has P plus. It has very little P minus. Okay. And the nucleus is going to the left. It has a very large P minus, but it has very little P plus. So then if I think of just form momentum conservation, in terms of form momentum conservation, where does the form momentum for this particle originate? Okay. Momentum has to be conserved, and P plus and P minus are, I mean, the plus and minus components are both positive. You cannot take more P plus, you cannot take more P minus from the proton than the proton has. And the proton has very little P minus. So this means that for this particle, this is why I scale it like this. the end result is that all the plus momentum of this produced particle, one way or the other, has to come from the proton. And all the minus momentum of this produced particle has to come from the nucleus. Because this one doesn't have any minus momentum, this one doesn't have any plus momentum. So kind of whatever ends up being in this produced particle has to come from plus from here, minus from here. Okay. And this is why I scaled it like this. So this is, this I will call XP. So this is, and this I will call XA, okay? So this is now all the plus momentum comes from the proton, and this is the fraction of the plus momentum that is coming. Sure.
I did just want to ask, so the way that we're treating the coordinate system now, it's effectively the plus and minus, we're just treating it, we're thinking about it as just moving along the same axis.
Yeah, yes.
In different backhands. Works surprisingly well, I guess it's constructed.
Well, it's kind of the incoming particles are exactly on the same axis.
Yeah.
The outgoing particle has a transverse momentum.
Hmm.
And of course, that transverse momentum somehow comes into play here. It's a little bit the same as we discussed yesterday, that somehow if you wanna somehow the small x limit is a limit of a fixed transverse momentum, and then the collision and the beam energy getting infinite. So here we're also we're going a system where the incoming particles are in the beam axis, and somehow there is some, okay, so the nucleus and proton as a whole do not have transverse momentum.
Yeah.
Maybe there are ingredients within them that do a little bit. And that's in some sense what we will get to. In some sense, what we will get is that we will be thinking that the KT actually comes from internal KT of the quarks and gluons inside the nucleus. But we're not really there yet. Now it's just thinking about how much of the overall energy of these guys do I need to produce this kind of particle. So this I call XP. So this is the fraction of the proton energy. And you see that I'm looking at positive y, k perf is and k perf is something. And when I go to positive enough y, when I go to enough forward for any given kt, this is going to be a number that is relatively large. It cannot get more than 1 because I cannot take more plus momentum from the proton than I have. So that puts a kinematical limit. For a fixed y, I cannot go to arbitrarily large kt. For fixed kt, I cannot go to arbitrarily large y. There's an upper limit. But anyway, here we are typically talking when y is large, y is positive 3, 4, 5, and kt is 1, 2, 3, 4. We're talking about numbers that are close to 1. And 1 is the upper limit. That's a cutoff. Whereas here, downstairs, I have a p minus over a, so this is a similarly large number, scale number. K perf is a 1, 2, 3 GB scale number, but then this gets much smaller than 1. Right. So this is the configuration we're looking at, where we're looking at things where XP is where from the proton we're taking something that carries almost all of the energy of the proton, or a significant fraction. Whereas for nucleus, we are looking at some degrees of freedom in the nucleus that carry very little fraction of the longitudinal moment. Okay. So this, of course, means that you can already guess that we will be treating the nucleus as a gluon field, because we are just at small x in this kinematics that we decided to look at this process. And then the proton, we are going to treat this as a valence quark. So we are going to be looking at the scattering of a valence quark from the proton on a color field.
Just want to ask, you say p minus of protons close to 0, but it's non-zero. I'm just wondering, why is it 0? Because the proton is moving in this direction.
It's zero if I neglect the proton mass. It is so. It is the p minus exactly is proton mass squared divided by 2p plus. Okay. So often you can neglect. I mean, usually you neglect the proton mass, but in order to be a little bit specific, it is a proton mass. So this p minus is mass squared over 2p plus. If the transverse momentum is zero and the proton transverse momentum is zero, it's a beam in the beam. This is strictly speaking, it approaches zero. Typically, often one neglects the mass and just takes it to be zero. And actually, in some sense, that's what we're. Well, we're not really, now that we decided that we're going to study quark scattering, we will forget the proton and talk about quarks, so we don't somehow worry about the mass. But even if you do worry about the mass, you ought to take it to zero. Good. So we are going to study.
So for the valence quark, I kind of know that you have the proton and then you could have this parton distribution and you would do this valence quark and describe this. How, what should I imagine now for this big nucleus? Could you also write down some matrix element or something?
Well, again, it comes back to the question of yes, you will. We will want to write a matrix element, but that is a matrix element of Wilson lines, because we do not want to treat this gluon field as counting gluons. So we're not going to be using the language of collinear parton distributions for the gluon. But we will get a cross section in terms of Wilson lines, the 2-point operator Wilson lines, and you could, in some sense, you could use this as a definition of. We will get the cross section in terms of what is known as the dipole gluon distribution, for which you can, if you want, we're going to be working in a specific gauge, but if you can write down a gauge invariant, put in links and write down a gauge invariant operator definition for the dipole gluon distribution, which is the transverse momentum dependent gluon distribution. So in some sense, in that sense, we will get a somehow something that has a well-defined operatorial definition, although we're not going to really go into the well-defined, write it in a well-defined way, but you can if you want. The gluon dipole team. Good. So we're going to study the valence quark scattering. Valence quark scattering on a gluon field. Just like yesterday. I will erase
there is an electron.
Let me start. Okay, so now I'm actually gonna, in addition to classical fields, I will write down bras and kets. Okay, I'm doing fancy quantum mechanics here. So we have an incoming state for our problem. Now I forgot I can draw here. So now we decided that we're going to have a quark here. So we are going to have a quark. This is now going to be a quark. This is now going to be a quark here, and it's going to be scattering of somehow the gluon field of this nucleus, right? So we have now this is a quark with the scattering of the gluon field of the nucleus. Okay. So the gluon field, we're going to treat it as classical, but our quark is going to be a quantum mechanical particle. So we are going to be looking at the quark, which has some letter that I use, which has a transverse momentum and a longitudinal momentum and a color. Okay, so this is a single particle state in canonical quantization. It's the asymptotic state of our quark. So of course we are going to take this PT is really 0 because we're going to be using collinear. We're going to be using collinear factorization where this quark is just going along the direction of the photon. But I'll just keep the P verb here for a while. Just but remember, it's really going to be 0 at some point. We're going to take it to be 0. So this is our. This is the incoming. This is the incoming quark state. This is the quantum mechanical state that is kind of coming in from. So this is now at x plus equals minus infinity. In our infinite past, our system is going to be a quark in a single particle state. Okay. So then now we are going to use the iconal approximation for scattering of the color field. And one of the things in the iconal, you remember from the iconal approximation, although I'm not sure I emphasize it very much, is that the iconal approximation likes to live in transverse coordinate space. Okay. You think that we're looking at the Wilson line at a fixed transverse coordinate. What happens in the iconal approximation is that the way the high energy goes in is that the energy is high. So the longitudinal momentum of a particle is high, which means that during the scattering, during the interaction, the transverse coordinate of the particle does not change. So the particle actually, when it's going through the field, it stays at the same transverse coordinate. And it would be tempting to think that, oh, because the transverse coordinate stays the same, it doesn't actually get any transverse momentum. But that's wrong. And that's what we're going to see explicitly now, that the coordinate stays the same, but it does get some momentum. It's just that at high energy, it goes through the target so fast that even if it gets momentum, the momentum is not enough to deflect the trajectory so that it will actually change into a different coordinate. It's going to stay at the same coordinate, but it's going to get some momentum. So this iconal scattering is simple in coordinate space. So what we're going to do is that we are going to say that this in state is actually a linear superposition of it's going to be a linear superposition of quark states where the quark is at some where the quark is in a coordinate space state. You can perfectly well define this. I mean, you can this if you have a good definition, and you're usually when you do study quantum mechanics, you're always used to momentum space states, right? And except very elementary quantum mechanics, you do wave mechanics, but then when you get to quantum field theory and scattering, and you're always in momentum space. But nothing stops you from taking a state and taking a Fourier transform and writing it as the coordinates. Momentum space state is as a linear superposition of coordinate space states. Okay, and this is what is known as a mixed space state. Mixed space state because I still keep the longitudinal momentum, but I have a transverse coordinate, right? So that's the word mixed refers to longitudinal momentum transverse in coordinate. Okay, good. So now, what does my color field do to what does my color field do to this kind of a quark? So now I have I'm gonna redraw this. Now I have a quark which is going through the color field. It's coming in with a color state I. So I'm going to introduce a little bit of notation, abstract operatorial notation for what this color field does. I am going to say that after this color field, x plus positive, or if you want x plus going to plus infinity, the system of my scattering particle is going to be given by the incoming state times multiplied by an operator S, which is the scattering operator. Now, this is a very general notation. This scattering operator could involve all kinds of interactions. If I go higher order in perturbation theory, this is going to include this quark emitting gluons and so on. But now at this order that I'm working with, the S is only somehow the classical field. What does the classical field do? So this we already know from yesterday. What does the classical field do? It just rotates these coordinate space states in color space. So now the S operator acting on a coordinate space state, a quark at coordinate x perp and p plus and color I is going to just trying to get the indices in the right order. And always, I'm probably getting a Wilson line and a Hermitian conjugate mixed up somewhere, but at least this is what I wrote. I hope it's right. There's going to be a Wilson line. So this is the Wilson line from yesterday. It's a color matrix, NC times NC matrix. And so it has two color indices, which I'm trying to write down explicitly. So remember the definition of this Wilson line is the exponential path ordered exponential e y plus a minus from minus infinity to plus infinity. And these are NC times NC matrices because it's a color field. So the Wilson line is an NC times NC matrix. I'm writing down the indices explicitly. Yes.
And would the gauge field is integrated over y bottom plus?
No, it's y upper plus. I hope. I might have written it wrong yesterday on the board.
You certainly wanted to write.
I certainly wanted to write y plus, and tomorrow I'm going to change coordinates again. But somehow we are looking at, and the way to remember here is that we are looking at the probe which is going in the positive direction. And the Wilson line, I mean, you shouldn't think in terms of pluses and minuses. What you should be thinking of is that this is a Wilson line along the trajectory of this particle. And the particle is going in the positive direction, so it's going along y plus. It has a color current in the y, which has a plus component, and that plus component of the color current couples to the minus component of the field. I might have I'm sure I made typos. I don't remember exactly which typos I make on which days, but it's going in the plus direction still today. Okay, so that's our Wilson line. So Wilson line, you remember we integrated from minus infinity to infinity. We discussed this in the tutorial session that it doesn't actually depend on that the Wilson line doesn't depend on the x minus coordinate, which kind of here, okay, so I will get to that in a second. So Wilson line at the transverse coordinate, we're saying that the Wilson line doesn't depend on x minus, and then this is just a linear superposition of quark states at the same transverse coordinate at the same and then in a quark state in a different color J, right? So this is just the scattering with the classical field turns the particle into a linear superpositions of particles with different colors, but everything else the same. Now here's another kind of interpretation of why the fact that the Wilson line doesn't depend on x minus. It means that if you Fourier transform, the Wilson line is a delta function in p plus. If you Fourier transform from x minus to p plus, the Wilson line is a delta function in p plus, which means that the target color field is not giving you any plus momentum. which means that the plus momentum of the guys coming out of the scattering is the same as the plus momentum of the particles coming in the particles. These quarks, all of the plus momentum they have, it's another reflection of the idea here that all the plus momentum that these quarks have that are produced is coming from what they had before they came in. And they're not gaining any plus momentum. And that's again a feature of the Eikonal approximation. Good. So now we have our outgoing state. And we're basically done. We're almost, we have the outgoing state. It just remains a little bit of conventions and figuring out Q's and pi's in order to get a cross section from this. But basically the problem is, the physics of the problem is solved. And just for the fun of it, I'll try to actually write the equation that you need to do this. I think I have 2 then pi's right. I might not have i's and sines right. So this is we know what the outgoing state is. What we want to do is to calculate the cross section. To calculate the cross section in the scattering amplitude. If you have done particle physics or quantum field theory, you have done this in a way that is almost the way I'm doing it here, but not exactly. So this is why I'm going to write a formula that kind of looks vaguely familiar, but is not exactly what you have seen. I assume that you have seen if you have taken a particle physics course. So I need an invariant amplitude, and my invariant amplitude is following the seminal paper of Björken, Kogut, and Soper is normalized in the following way. I split out this factors by delta function of p plus minus q plus, and then I have my invariant amplitude for color I and transverse momentum P going into color J and transverse momentum Q. So this is my invariant amplitude, and my invariant amplitude is related to the matrix element of a quark state. So now the final state is Q perp, and the color is J. And since this plausible momentum is conserved, I'm somehow abbreviating a little bit and leaving it out. This S hat operator -1, and then the incoming state P perp and color I. So that's such a formula where you write matrix element and is equals invariant amplitude and some delta function. I assume you have seen something like this, right? You have probably seen it in a way where there's a 4-dimensional delta function here, right? Here I only have a 1-dimensional delta function with a plus component, and the reason is that this is an invariant amplitude for a slightly different formulation of the process. This is not an invariant amplitude for a 2 to n scattering. This is an invariant amplitude for 1 to n scattering of an external background field. So this means that, of course, form momentum is conserved, but in this problem it kind of doesn't look like form momentum is conserved because the external field. And my approximation is that the external field doesn't give you plus momentum, but the external field can give you transverse momentum. And because my outgoing particle is going to be an on-shell particle, if the external field gives me transverse momentum, the external field has to give me minus momentum too, because the minus momentum has to come from here. I'm not kind of keeping track of the minus momentum. I'm just somehow thinking that, okay, this is a high energy nucleus going in the minus direction. it has lots of minus momentum. So it's just gonna give this particle as much minus momentum as it needs to get on shell. Okay, and I'm not keeping track of the minus momentum, at least at this point. I'm just saying that there's enough here to make this go on shell. And but it's going to be, so I'm going to get transverse and minus momentum from the target. This is why only plus momentum is concerned. And of course, you remember, if you have seen this kind of formula, you remember why it's factorized like this. It's because we're going to have to square this, right? And you have to square a delta function, and the square of a delta function is a delta function at 0 times a delta function. And then the delta function at 0 is absorbed into kind of how the cross section is defined, right? The cross section is, you have to put your particles in the box and normalize by unit volume, and normalize the volume, have some interval in time. I mean, there's this the kind of the standard thing that you do in a particle physics course. You do it here too, and I will not do it, but I will somehow just claim that okay, it works in a similar way. I mean, so, and that's why you have to factor out. That's why you have to factor out the delta function. You also factor out a 2 pi that always goes with the delta function. You always also factor out the 2p plus, which has to do with the way things are normalized in a Lorentz covariant way. I know, remember that kind of our Lorentz covariant phase space measure is always dp plus over p plus. Okay, so in some sense, it's a 2p plus 2 pi delta function of p plus is the natural combination that the field was. That's a Lorentz invariant way of doing things. Good. So this is the invariant amplitude. So before we calculate the cross section, let's calculate the invariant. Let's calculate the invariant amplitude. I will
Sorry, I just have a question.
Yeah.
I just want to ask, so we've made the jump from, okay, we want to deal with a proton interacting with a nucleus. Okay, at a high enough energy, it's basically a valence quark with background field. Why does the proton now have color? How wide are we motivated?
Well, the valence quark always has color.
Yes.
And now we're treating the proton as a conduct, as really in the part one model, that as a bunch of almost non-interacting colorful quarks. So the quark has a color, and we are having what we in terms of the resolution, we're looking at processes where the transverse momentum is high enough that we're not actually seeing a proton scattering as an intact proton, but we're looking at a high enough transverse momentum process, 123 GeV, where you see where the resolution scale, our wavelength is so small that we do see the proton as consisting of point-like colorful particles.
And you're interacting with one of them.
You're interacting, I'm interacting with one, and then at the end, I will somehow go back to the whole proton and the PDF. Okay. Good. So let's calculate. Let us calculate this. Let us calculate this matrix element. Good. So all this matrix element star, and we're just gonna plug things in. So now we need the incoming. We need an incoming and outgoing. These are two momentum space states. Both of them need to be written in terms of Fourier transforms. So I am going to have two Fourier transforms, expert and a Y-perp, right? And do I choose? Is this the point where I take this? This is the. No, I'm not taking yet. This P-perp I had. I'm not sure I'm fully consistent, but let's with myself. But here I had a plus I, and the other one is in the complex conjugate. So I'm going to have it. So yeah, so plus I. The other one is a complex conjugate, so it's going to have a minus. So I'm going to have a minus I Q perp dot Y perp plus I P perp dot X perp. And then I'm going to have this B J I at X perp, and then I have to subtract the one. So why the one? This is the same thing as yesterday. You have to subtract the incoming wave. So somehow this S operator is such that if there is no background field, the Wilson line is 1, and then my scattering amplitude should be 0. That's so S minus 1 is what gives me the scattering amplitude, and it's going to be an annoyance that we get rid of pretty soon. Slightly funny way. Okay, and then what I need is just the. Now I'm going back to coordinate space. Yes, so I have a Q of this is a Y perp and color J, and Q at X perp and color I. Now I have this, I'm doing something crazy here. Yes, I'm doing something. I'm mixed up with my colors because I don't want my incoming particles to have the yes. Well, this is I should be a little bit I should be a little bit more careful. Here I have a color J, so I actually have to I mean here I have a color J, so let me change this J into a color K, and the color K, and the color K, right? And then this is a K, and this is a J, and now this is a K, because my outgoing state is a sum over the color K of states with K, like this. Yes. And so here you see that somehow what yes.
And then the sum.
Then the sum over K. Yes. So here you see the kind of the simplification. Yes.
Is there any reason why our Wilson line multiplies our wave function from the right? With the way the indices of the actually written.
Third equation from the bottom.
It's just
BKI, it looks like multiplying with the transpose matrix or multiplying on the right.
yeah.
Which is fine.
I think it's the way there are different there's a convention and it's in some sense the way I think of it is that because this is actually the way I think of it is that you're coming in with K, right? And so it's the indices here are incoming and outgoing. And this is the outgoing. So it kind of looks like these are the wrong ways, BKI times. It doesn't look natural in terms of a matrix multiplication. But if you think of it this way, that it's an I to K. It's an I to K, and this is the K, and this is the I. But different people have different conventions, and I'm not sure I'm even consistent with myself.
If you've seen me write this, I would have written it differently, but.
Yeah. And some people, I might also write it differently on a different day. For some people, the dagger is the fundamental object, at least for Edmond. I'm not sure about her. I find it funny that the dagger would be the thing, and he just the conjugate of the dagger. Good. So what I was saying is that kind of the operation now turns, this operation kind of turns the interaction with the target into something trivial that passes through, and then the expectation values of the quantum mechanical states are just somehow simple orthogonality relations. And you can easily see, but I will that also the coordinate space states are orthonormal in the same way as momentum space states. So this inner product is just it's a Kronecker delta. It's a E plus minus Q plus, so the longitudinal momenta that I didn't even write here. And then this is a two-dimensional delta function of x perp minus y perp, right? So what I get is that my so there's a two-dimensional delta function. I get rid of one of these integrals. There's a sum over k, but there's a orthogonality between the states means that I can sum over k. And what I finally get, plugging this into here, and then you see that this 2p plus delta 2 pi delta function goes away in that's the thing that is factored away from the m. So kind of my states are normalized in such a way that you always get this factor from the orthogonality of the states, and therefore they cancel away. And what you end up with is a matrix element, which is very simple. The matrix element is just a integral, a Fourier transform of I here down. So this y becomes the same as x, but there's still a minus q. So p perp minus q perp minus x of the Wilson line. My indices are k becomes j, so ji and when ji at coordinate x minus delta ji. So now I've calculated my scattering amplitude. And again, as kind of promised yesterday, what again this is shown that what the Wilson line is, it's a Eichel scattering amplitude. I have a properly normalized scattering amplitude, which is just because I'm interested in momentum space states. I want to measure the momentum of this guy. My amplitude is just a Fourier transform. So and my amplitude is a Fourier transform, and this again also kind of shows again what I said is that in the Eichel approximation, the particles stay at the same coordinate when they interact with the classical field. That doesn't mean that their momentum doesn't change. It's the Fourier transform of this coordinate dependence gives you the momentum transfer. This is the momentum transfer that the particle gets from the target. Good. So before we take a break, we'll just write down a formula for again general. I was so happy that I even managed to get the normalizations right. So I will again write the other formula that I just take. So as you remember, you have seen this expression somehow that when you factor out the delta function like this, you need to go through a little bit of machinery to get from the square of this amplitude to the cross section and the cross section and this. So in this case, you do you go through this calculation in an not exactly the same way as you have done in particle physics, but in an analogous way.
The bigger ones.
In an analogous way. And the result is that the differential cross section is going to be okay. So what I have a 1 over NC sum over I and J, y 1 over NC. Remember, I'm averaging over incoming colors and summing over final. Average over incoming, sum over final. So this is summing over the colors of the incoming and outgoing quarks, and 1 over NC because I want to average over the incoming. And then a 2e plus 2 pi delta e plus minus e q plus. And then my matrix element squared, and then the Lorentz invariant phase space, e squared q curve over 2 pi squared d, let me call this b plus, this is over 2t plus 4p plus 4 pi p plus, and that's it. So this is another formula that, to my knowledge, for this kind of a case was the first time written down in Björken code software. Although they say that, and this is at this point Björken and the company write that, okay, and so any field theorist is quickly able to take this and derive this formula, and so he doesn't give any details, but somehow it's quite credible because you have done the similar calculation in many cases. Okay, so and then if I plug this, I'm gonna.
What you're hiding is the I's and the J's.
What I'm hiding is the I's and so let me write the I's and the J's. Let me write the I's and the J's. And just take this matrix element, and I will write the 1 over NC sum over I and J of m squared. So I'm gonna have a 1 over NC sum over I and J, and then I have to square this again. Oh, by the way, now I'm taking d per equal to 0. Just to make my life simpler, I'm taking the incoming quark to 0. I promised I would do. I'm taking absolute value squared of this. So now I have again an integration over 2 coordinates. Perhaps confusingly, I will call them x perp and y perp. So from this and the complex conjugate, I took p perp to 0. My incoming quark has 0 momentum, but I still have the q perp. And now the q perp appears, which is the produced work. Now the q perp appears in the amplitude and the conjugate. So I have an exponential of, maybe I should call this minus I q perp x perp minus y perp. Okay. And then I have a times b ji at x perp. Then I'm gonna go combine. So I have a square sum of 2 terms, and I'm squaring that, so I get 4 terms. I'm gonna do already simplify the sum. Then I'm taking the Hermitian. I'm taking the complex conjugate of bji. So the complex conjugate is the same as the Hermitian conjugate of the transpose. Right? So I'm switching indices and I'm changing, writing a Hermitian conjugate instead of a complex conjugate. So this is ij and y perp. Okay, and then the other terms just have delta functions. So there's a minus j I at delta ij. So this is a delta b j I times delta ij. So this is just an I at x perp minus b angular I at y perp, and then plus the plus delta I J. Like this. Okay, so here, what I'm gonna do next is I'm gonna do some arguing a little bit. So I'm integrating over X perp and Y perp. Okay. So I have a Fourier transform from X perp and Y perp to Q perp, which is the momentum of the produced particle. In all of these terms, there's no dependent, all of these terms are such that there's dependence on one of the two coordinates, but not the other. So for example, here I depend on X perp but not on Y perp. So I can do the integral over Y perp, and that gives me a delta function in Q perp. Okay. So all of these terms are going to be proportional to delta functions of Q perp. And what this means in terms of my original scattering, I'm calculating a scattering where this produced particle has a momentum Q perp. So this is not giving the produced particle any momentum. Okay. So I will just, these kind of need to be there for the whole thing to be unitary, but they're not physically interesting. So I'm just gonna throw these away. They're not contributing to the cross section I'm really interested in measuring, which is required that the produced particle actually has some momentum. So here, on the other hand, the essential thing is sum over colors and this thing. So this is what I call the dipole operator. One over MC space P of X perp integral at Y perp. Okay. So now I've written my cross section in terms of something that I call the dipole operator, and this is gonna, these dipoles, when Matt gets to high energy QCD, these dipoles are gonna be all over the place, and these dipoles are gonna be all over the place in the rest of it for a lot of my remaining lectures too. Here, I think it's time for a 5-minute break, and then we'll talk a little bit more about this and also about extending this calculation a little bit.
Very good.
5 or 10 minutes. 5.
What do you feel like? Your choice.
Okay, let's take 5, but then it's going to be lighter. I'm not going to be calculating it already after that. So. Okay, so let's continue. So after a lengthy
Question. So now we have this cross section formula, and so to get from this formula to this plot, we would now convolute with
I would convolute with the PDF and the fragmentation function. Because this is single, I'm calculating quarks, and this is a single charge happens. And that's actually that's all there is to this curve. It's this formula plus a PDF and a fragmentation function. I mean, and then somehow, of course, the physics is in what is this?
and what do you do for the gluon field in this?
Well, for the gluon field, I do is that I express the deep inelastic scattering cross section in terms of the same observable. I do BK evolution, which tells me the energy dependence of this dipole operator. Armed with the BK evolution, and some I fit Hera data. I fit the initial conditions of this BK evolution to Hera data, and then I take the result and I plug it in here, and I calculate, and that's what gives the new. And then okay, so I have Hera data, and then of course the nucleus I do optical Glauber to extend from a proton to a nucleus. And so which involves basically just the Wood-Saxon parameters. What the only thing that in non-trivial thing there is it involves the nuclear thickness function. What is the radius of the nucleus? What is the density of the nucleus? Which is kind of low energy physics. To go from a proton to a nucleus. So those are the ingredients I need to get there.
For this violet.
This is for the violet.
And there's no uncertainty on this line because it's hard to estimate that.
Well, it's hard to estimate the uncertainty. There's no NLO calculation. Well, there's no workable NLO calculation. Fully workable NLO calculation. Hera data is very precise. So if you fit Hera data, it doesn't. If you fit Hera data, fit small X Hera data, it gives you a very. It doesn't give you a statistical error because the error is so small. So if you get a good fit to Hera data, but there's also I think the biggest, if we would do a scale variation in the PDF and fragmentation function, that would give us a better plan, but we don't do that here. But also the scale variation to a large extent cancels out in the ratio. Right? It's a nuclear proton ratio. That's one of the reasons why it's, from a theorist point of view, it's nice. Right. Scale uncertainties in fragmentation functions, PDFs, a lot of this, not completely, but to a large extent cancels out. So the big error band here, this is polynomial factorization. That is just the big error band here reflects the fact that existing nuclear DIS data has large error band, has large errors, and therefore when you do a PDF fit to nuclear data, you get a large error because that reflects the error in the experiment. We don't go to nuclei by fitting nuclear data. We go to nuclei by optical Glauber. So just taking a thickness function. Yeah.
So are you not calculating these Wilson lines like are you fitting the Wilson lines what are being?
Well, we are getting the Wilson lines. So there's different ways of calculating. So far I haven't calculated the Wilson lines at all. I'm somehow. So there's tomorrow we're going to do a model, the MV model, the McLaren-Benning-Goplan model, which is a one parameter model that allows you to calculate this. And then there's one parameter you need to fit. You need to take the value of this parameter from some. The other thing you can do, which I hope Matt will do, I will not this time, is that, as I said, you can derive a renormalization proof equation for this dipole, right? The BK equation, or for the Wilson lines, which is the Jim-Watt equation.
Then how do you choose the starting point?
And then, but then these equations tell you the energy dependence, the rapidity dependence of these things. So you need a non-perturbative initial condition, which again ultimately you have to parameterize and fit to something. So there's always something in QCD that you have to get from some experimental data. With public QCD, you cannot calculate everything. You can calculate the dependence on something once given a non-perturbative initial condition that you need today. And then you can express the deep inelastic scattering cross-section in terms of this same quantity. And then you can compare, okay, I calculate deep inelastic scattering cross-sections, I can see whether my dipole operator fits that. Then I can use the same thing here. And then again, I hope Matt is going to go into this DIS. But it's the same. The same dipole operator will. I'm sure it will appear at some point in Matt's lecture. Yes. And kind of this is the division we a little bit decided that I will do a PA and he will do DIS. But it's the same. It's the same thing will appear here. The funny thing is, well, I'm going to a little bit steal from Matt. What is going to happen with Matt, and what kind of the thing that you might have heard from Heribert, you have heard him talking about this, is that in DIS you have a virtual photon which splits into a quark anti-quark dipole, and that's the dipole. This is the interaction of this dipole with the target. In the way you do the DIS calculation, there's a dipole in the amplitude, both the quark and the anti-quark are in the amplitude. Here, you remember this came from a quark in the amplitude and a quark in the conjugate amplitude. So this is a dipole, and a dipole is a quark anti-quark state. But we have a quark anti-quark state, which consists of a quark in the amplitude and a quark in the complex conjugate amplitude, and the complex conjugate of a quark is an anti-quark. And here we have a dipole. So this is a quark and conjugate at different coordinates. We are interested in a momentum space observable, so we are Fourier transforming. When you do deep inelastic scattering in this formalism, you don't actually go to coordinate space. You don't go to momentum space, you stay in coordinate space. So you don't, so you have the data. So somehow you naturally express the cross section in terms of the same coordinate space observable without Fourier transform. So here, whereas here we're looking at momentum space observable, so that's probes the Fourier transform of this operator. Good.
Another question.
Yes.
I might be jumping the gun here, but is there an easy mathematical way to see that this dipole operator is translation theory?
No, and somehow in general, it's not mathematically translation given. Here I haven't really specified. I'm just gonna have told you that this is a color field of the target. I haven't told you anything about the target. So whether or not it's translationally invariant depends on whether the target is translationally invariant, right? And it really depends on the physical system. And sometimes the target is big. You can approximate it as being translationally invariant. You can also try to use this formalism for targets that are small when it's not necessarily translationally invariant. So it depends on the physical system. Okay. Typically you would, and I haven't also typically somehow a target in the end there is some quantum mechanical state. So you're going to have to take some kind of an expectation value over some kind of degrees of freedom in the target. And often it is the case that on a configuration by configuration basis, it is not translationally invariant, but maybe the expectation value of over some kind of properties or some of the target is translationally invariant. And I haven't said anything about this kind of expectation values. Tomorrow we're going to do expectation values like this in the MB model. So that's going to be a specific classical model with a classical stochastical model that allows you, has fluctuations, but over which you can take expectation values. So we're going to do an explicit calculation of this kind of stuff tomorrow.
Okay, so why is it fine to then write it as a function of x per minus y per?
Oh, good point. So that here I'm going ahead of myself. Let me okay. I was getting ahead of myself. Often you take it to be a translation invariant, but in principle it doesn't need to be. It's depends on the physical situation. Good. So I somehow hopefully correctly put together all the pieces, and let's do one more. Let's do one more thing, which is to introduce go from valence quarks to protons. Okay, so there are a lot of Q pluses floating around. Let me just remind you that dq plus over q plus is dy, right? So I'm going to, this was differential in q plus. There's a overall, after several cancellations, there's 1 over q plus here, so that I can multiply this up, and it goes like q plus over q plus, and which is per unit rapidity. So somehow this is how things naturally always come. You get cross sections that are differential in rapidity. So now let me go from this to a cross section. Here I have a quark nucleus going to quark plus anything cross section. I will go to a proton nucleus going to quark plus anything cross section. And I will keep it differential in the quark. And now I will make it differential in the rapidity. And so the way I will do this is that I will say that, okay, now my quarks are coming from, they are valence-like quarks. Okay, so they are coming from something for which the parton distribution function, or linear parton distribution function, is the correct way of describing them. And I just need to translate from this quark distribution to the incoming quarks. So what I will do is that I will integrate over the momentum fraction, and I will have a Borg distribution at some transverse moment scale. At this level, the lowest order perturbation theory I have. In principle, there's an x q squared here, but at this order perturbation theory, I have no control over the scale. If you do phenomenology, I'm going to have to put something there, but this is not under control in this calculation. And then, okay, so what is this x? So this x is a momentum fraction. So we're going to integrate over all the momenta, all possible momenta of quarks. And we're going to, again, here I'm inserting an identity. So I'm going to integrate over all quark momenta. So you see that this is just a identity. I'm integrating over all quark momenta and saying that my incoming quark momentum is the momentum fraction times the momentum of that. So this is now the momentum. Hold on. I switched from a small p to a capital P in the middle of my calculation. And then I just have this cross section d sigma quark plus nucleus over d squared q per dq plus. And then what I do is that I first, I'm a little bit of trickery, I first integrate over x using the delta function. So I take another chalk and I take this and this, and because I'm integrating over x, or actually I think this. And this, right, that's what I'm doing. No, that's not what I'm doing. Getting messed up completely. Let's take a step. Let's take a step back. What I'm missing here is the delta function of p plus coming in minus q plus going out. We have only q plus limit. Yes. Now sorry for this thing. This I was missing. So what I will do is that I will integrate over this. I will integrate over this incoming quark using the delta function that tells me that the incoming quark and the outgoing quark are the same. That's going to leave me with a p plus. With a p plus, and then I'm going to use then I'm going to write this delta function as a delta function of I'm going to take out the p plus. So I'm going to write this as a capital P plus delta function x minus p plus over capital P plus, right? And then I'm going to integrate over x. I'm going to, I already integrate over this. Then I'm going to, I have an integral over x, but then I have this and this, which is nothing but x. So I will have the color. I will have a dx x q x q squared, and then this then the 1 over 2 pi squared integral over x perp over y perp exponential of pi q perp x perp minus y perp times the dipole operator x perp and y perp. So I ate up this thing from there. Ate up this. This is my final result. Okay. So the only somehow point of this exercise was to the only point of this exercise was to go through the little detail that. So physically, once you have gotten to this point, this is very transparent, right? Physically, kind of you can see the ingredients. You're integrating. You're taking quarks from a quark distribution. You're integrating all the different possible momentum fractions that these incoming quarks can have, and then each of these quarks interacts with this cross section. The non-trivial thing plus here is you have a q plus times. You have a q plus here, and although you initially introduce when you introduce the quark distribution, kind of this quark distribution q is usually normalized in the way that is differential in x. You think of it as number of quarks per x, right? But because of this Lorentz invariant normalization, what you end up having is x times qx. And x times qx, the interpretation, why do you have x times qx, is because x times qx is the number of quarks differentially in rapidity. So naturally, somehow, when I talk to DGLAP guys, they think in terms of q, right, for distribution, gluon distribution. I think in terms of xq or xg, because xq and xg are per unit rapidity, and I'm kind of doing very boost invariant physics, where I calculate things per unit rapidity. Okay. So here, okay, and then in order to get this,
That's one more question.
yeah.
Okay, I'll ask it.
Okay, so and then in order to get to this point, to get to these curves, these are identified hadrons. So you need to do a similar exercise to go from the produced work to a produced hadron, which conventionally you can do by fragmentation functions, which are kind of in some sense analogously to the way quark distribution tells you how many quarks there are in a proton. Fragmentation function tells you if you produce a quark, how many hadrons does it produce? And the hadron gets a fraction of the momentum of the quarks. It kind of goes the other way. Now you have a question. Or do you want to come back to it?
I'll come back to it.
Okay, good. So this is known as the hybrid formula. So why hybrid? Because it's a very asymmetric way of describing things. There's a high x part described in terms of collinear factorization. There's a low x part described in terms of this dipole operator. And the dipole operator is an important thing for us. And you see curved, you can actually use this formula and use this formula together with a fragmentation function to actually calculate things and try to understand things about experimental. So a few things, and now kind of this is the end of kind of our calculation, but I will say a few things more. So look at this dipole operator, and from this dipole operator, this is enough to understand the essence of gluon saturation is here. So these are Wilson lines. They're SU3 matrices that come from solving a differential equation for the propagation, the Schrödinger equation for propagation of a quark Dirac equation, propagation of a quark in a color field. So let's look at this a little bit and go a little bit ahead of ourselves and now assume that the dipole is translational invariant. Let's just assume that we're looking at a big nucleus and it's translational invariant. We're taking some kind of an average over the internal degrees of freedom of the nucleus. So we're looking at the expectation value of this dipole operator. So if I call R the x perp minus y perp, well, let's assume that it's translational invariant. So first, look at R equals 0, so x perp equals y perp. So these are unitary matrices. So V dagger V is identity matrix, right? And there's a trace of identity matrix 1 or NC. Yes.
Sorry, I just want to ask, wasn't the point of V today when you found the delta?
Yep.
Wasn't the point of that to like somehow integrate out the hits?
Well, I I was confused. Yes, I originally was saying that I'm going to integrate out of x, but then I realized I was somehow doing this in a little bit wrong way. So no, you don't actually integrate over x. You use it to integrate over this to this p plus thing. And you are left. So sorry, I was confused myself, and this is why I told you. You are left with an integral over x, and so the cross section is kind of you integrate over x, and the proton has a different x has a different number of quarks given by the quark distribution, and the measured cross section is an integral over this. So this integral remains. Sorry, I was confused with my formulas.
And now that you started discussing it, but if you just integrate over p plus, where's the factor x?
I think essentially the factor x is in the fact that you have always have a q plus delta q plus. So this is kind of per unit rapidity. So this is a delta function in rapidity. So it's this q plus, which becomes this p plus, and then you write this into. I think I should be leading this delta x. I'm really confused with my really confused. I'm really confused with my interface. Do I have anything? You are right. I do integrate over x because I did have the delta function. What I have is this. I don't have an integral over x. And why? Why? Of course, it's because. Sorry. Yes. Thank you for pointing this out. It's because going back to the very beginning, we measure a quark with a fixed kT and rapidity. And the fact that we're measuring, we are calculating differential, or this is now qt. Change my. We're measuring at a fixed qt and rapidity, and of course, the fact that we're measuring for a fixed qt and rapidity, these completely determine what x is. Yes, sorry, I have the u word. I was again have to correct myself. These are fixed, so it means that these determine what the q plus of the produced particle is. And when the q plus is fixed, x is fixed. So I'm not integrating over x anymore. I have a cross section where when it's differential in this, x is fixed by whatever the transverse momentum or the measured particle is. Only when I start integrating over these, then it becomes an integral over the quark distribution. Yes. So there's a delta function. This is why I arranged the delta function to be delta function of x so that I can integrate over x. And now x remains with the understanding that the value of x is determined by looking at the kinematics of the produced particle. This hybrid formula was in this form that is used was derived basically in 2005. 15 years, maybe 20 years old, depending on which paper exactly we're back to. Good. So let's look at the dipole operator. It's a function of r. So at x equals y, identity matrix, trace of identity matrix is NC. So this starts at 1. Right? Then on the other hand, I'm going to be taking some kind of an expectation value of this dipole operator over some kind of internal degrees of freedom there. And if I take 2 points x and y that are very far, the Wilson lines should be uncorrelated. I should not somehow have color fields 10 per or a meter away from each other, knowing anything about each other. So at large distances, this should any kind of an expectation value should factorize into an expectation value of the products. And it turns out that if the expectation value of your single Wilson line, the only gauge in that thing that it can be is 0. So actually, at large distances, this kind of operator will go to 0. So as a function of r, the dipole operator is going to look like this. It is fixed to 1 here, and it is fixed to 1 here, and then it goes to 0. Now, and this is a function, so kind of on a very generic grounds, we expect that this is a function that interpolates between 1 and 0. And what that means is that there's a characteristic scale. Right, I can choose some value, let's say 1/2. Some kind of value of between 1 and 0, and I can say there's a point where it crosses. There's a point when it crosses this value, and somehow for larger r's this is kind of small compared to 1, and for smaller r's this is close to 1. Yes.
Is it monotonic like that?
Well, in principle, that it doesn't need to be, but it would be weird physically if it was not.
You would need something interesting to happen for it not to be
Something weird.
monotonic, right? That's so if you discover that it's not monotonic, you have something really interesting. But in a generic system that has no features a priori built into it.
So we choose 1 as sort of like to normalize the scale. That's how we know that it takes values around 1.
It's the 1 comes from here. The 1 comes from the fact that these are SU3 matrices.
SU3, okay.
And and somehow the 1 is, in terms of scattering, the 1 means that the scattering amplitude is 1. In terms of a dipole scattering, it's a dipole scattering of the target. It means that you're scattering, like in optics, it's like scattering of a black disk. It is kind of a completely absorbing thing. So it's really so what is here kind of in something that is unitarity requires that scattering amplitudes cannot be arbitrarily large. Here, these unitarity requirements are built in by the fact that we're using Wilson lines, and these are SU3 matrices, and they're on the group manifold that gives us some constrictions, somehow restrictions on what kind of values this kind of thing can take. And those restrictions that is so kind of it's built in. Unitarity is built in, and also saturation is built in. And so saturation is kind of a result of unitarity, because when you have something that interpolates with, and so what any kind of a perturbative calculation will give you, the perturbative calculation in a theory with only point particles would always give you some power. In fact, in this case, the perturbative calculation would tell you that this dipole goes like 1 minus r squared times maybe logs, powers and logs. So a perturbative calculation will give you something that goes like this. Right? And it just goes on and on. So a perturbative calculation will give you purely perturbative 1v1 exchange calculation will give you something that is not admissible as a trace of SU3 matrices. So this means that somehow the fact that these are SU3 matrices, at some point they have to deviate from what the perturbative expectation, and the place where they deviate is somehow 1 over QS, and QS is the saturation scale. So in core, and then the other thing, we're constantly going back and forth between coordinate and momentum. So you can think of the saturation scale as a coordinate, as a 1 over QS is a length scale, or you can think of QS as a momentum scale. These are two sides of the same coin. And depending on the observable, we're going back and forth between coordinate and momentum space. So I think we'll have more to say about saturation in the coming days, and we'll calculate this in an explicitly in a model in the end. So another thing that I will try to do is a sketch of. So the question is, what could you do? And so this is kind of where the state of the art is. What would you do to go to higher orders in perturbation theory? So what would NLO look like? So let me just draw one picture. So we had a quark, and we treated this quark as a quantum quark, went through the classical field. So what happens if this quark emits a gluon? Now this is a quantum gluon. It's really a quantum gluon emitted by a quantum quark. I can do light cone perturbation theory. My preferred way of doing this is light cone perturbation theory. And then this quark and gluon. Yeah, I could use another color. This quark and gluon are both together going through the color field of the target. Okay. I could, for example, then I could do armed with the additional. Now I was in this calculation, I just had single particle quark states. But when you know how to do perturbation theory, you can go from single particle quark to quark gluon states. And I could do exactly similar calculation, except that it just gets more complicated, but somehow conceptually very similar calculation for calculating the square of this kind of a diagram, where a quark first emits a gluon, and then both the quark and the gluon propagate through the classical field. I could do this. I could calculate a cross section, which is differential in both the momentum of the quark and the momentum of the gluon. Okay. Such a cross section in kind of this language, actually, at least in this language, was first calculated by Cyril Marquet in 2007. Somehow, at least that is my go-to reference. And this cross section. Okay, so let me somehow very schematically. I will not write down the equation, but what you see is that what this cross section involves are both quark and gluon going through the color field. Now, the gluon is in an adjoint representation. So quark is in a fundamental. So the quark will give you a Wilson line in the adjoint representation, in the fundamental representation. The gluon, you can write it in different ways, but the way I like to write it is that the gluon gives you an adjoint representation Wilson line, just a different representation because it's a different color particle. You can write the adjoint representation matrix in terms of two fundamental representation matrices. As a Hertz identity that allows you to do that. I can give you the formula if you want to know, but since we're not doing calculation, I will just tell you that you can express an adjoint representation matrix in terms of, well, I can write the formula. I hope I get it right. An adjoint representation matrix components A and B is 2 times trace TA B E B B dagger, where these are the fundamental representation generators that have, there are 8 of them. So with this kind of an identity, you can go from between adjoint and fundamental representations. Okay, so I will have in the amplitude altogether 3 Wilson lines. Then I square. In the same way as here in the amplitude, I had 1 Wilson line, I squared, I got the dipole, the conjugate amplitude. I will get, so when I square, I will get up to 6 Wilson lines. Okay. So this means that my expression for the cross section will involve Wilson line correlators up to 6 Wilson lines. It turns out that there's no sextupole, so-called sextupole, but there are dipoles and quadrupoles, where this is now the same. This is the same dipole, and a quadrupole is a trace of the dagger at some coordinates. So I will get cross section for this kind of process will involve operators of up to 6 Wilson lines. For example, in the form where there's a dipole correlator, and then a quadrupole correlator. It's kind of somehow always nice to arrange these into traces, which are kind of gauge invariant. Yes, you will treat invariant objects. You can write this in many ways. Okay, but yeah, for me, it's most convenient to think in terms of traces. There are dipoles and particles. So it's a more complicated expression that goes into more detailed aspects of what these color beams, what these Wilson lines are. So this, once you do this calculation, you can go into two different ways. You can either integrate out the quark or integrate out the gluon. So you calculate the production of two particles, then you integrate out one of them. This is a part of then this kind of a calculation becomes a part of an NLO correction to single inclusive particle correction. So it becomes a higher order correction to the process that we were calculating here. Right? So this, and then of course there are other NLO corrections. And there's a radiative and virtual that you have to. And these NLO corrections have been calculated. There's been a lot of they have been calculated, they have been compared to data, but there's been a lot of renormalization and factorization gets tricky. So there are kind of technical issues that are kind of, well, I think they're solved, but people don't agree on what the solution. They have been solved, but people don't agree what the solution is. So it's still a little bit of a discussion in the field of what the I think everybody agrees at this level, but the problem comes later. I mean, when you the problem comes to a different part of the calculation when there's an additional divergence in this integral that you need to absorb, and then this there are some delicate issues there that are still topic of discussion. Is a part of the NLO next to linear or single inclusive. One important thing about this, some part of this kind of a next to linear or calculation comes from a region where this quark and the gluon are collinear. So there's a subset of, we are integrating all the phase space. Some subset of this phase space is a collinear region. So for example, when Q perp goes to 0, a collinear region, and that collinear region leads to a infrared divergence, leads to a collinear infrared divergence. And then what you do is that this collinear infrared divergence is absorbed into D-glap evolution. So you take this, you calculate a piece of the next to leading order in some specific part of the phase space where this is. It gives you a divergence. And what you do is that you look at the leading order result. You say, but my leading order result has a fork distribution function. Let me renormalize this fork distribution. I will take this divergent piece of the NLO. I will move it over and put it together with the leading order piece. And then this leading order piece becomes a renormalized fork distribution. And then this leads to D-glap evolution. You factorize this particle beam divergence, absorb it into the renormalization of the fork distribution, and as a byproduct, you get D-glap evolution of the fork distribution. So that's somehow, in some sense, if you ask for proof of the hybrid formula, in some sense, the first step of proving that this formula is correct is calculating the next to leading order, calculating some parts of the next to leading order correction. For example, you can calculate this part of the next to leading order correction, and you show that the divergence can be absorbed in the D-glap evolution of the fork distribution. Only then you really know that kind of this is the fork distribution and not something else. Right? So you need to, in order to prove this formula, you need to calculate higher order corrections to it and show that they happen, work in the right way. In a similar way, when this gluon becomes very soft, when this longitudinal P plus momentum of this gluon goes to 0, so Q plus going to 0, I would call. I think soft is not exactly that. I think Thomas, I think for soft would require Q per and Q plus to go to 0 at the same time. I will in an abuse of language, I will just say that Q plus going to 0 is soft. That naturally is a little bit non-kosher. That leads to Jim walk or EK evolution. So this part of the NLO correction leads to Jim walk or BK evolution, which is the evolution that tells us something about how this dipole operator depends on energy. Yes.
Right now, when you say collinear and soft, are you referring to types of similarity?
Yes. Yes. So this is the singularity in a very concrete sense. You calculate this. It's a function of K perp and Q perp, and of course of the rapidities. And then you say, okay, I have a function and I want to integrate over this Q perp. And there is a singularity in this integration in the region where the transverse momentum of this gluon becomes small.
Right. It's just like the rapidity, the similarity which actually manifests in a Jim-Walk evolution. They're due to logarithms of 1 over yoke x.
Yes.
Which people arrive to they're essentially a rapidity separation. So I'm just curious as to like how you relate that to the softness of energy.
There's a detailed discussion and a quick discussion. Let me give it a quick discussion. We can discuss the detailed discussion later. The quick description is that the divergence looks like this, and this is just this is dy rapidity. So this is an integral over rapidity from minus infinity. So this is a rapidity. This is a rapidity divergence. Which goes to Jim-Walk. Just depends on whether you write in terms of Q plus or in terms of rapidity. But there's a mapping between the two. Okay. So this kind of a correction, it gives you somehow you go into the direction of next to linear or corrections. Then there's another avenue that this kind of a thing leads to is that you say, okay, I calculated two quarks and a gluon. Why don't I measure 2 particles? And this is kind of a conceptually also very important measurement. So you can measure 2 particles. Then you measure 2 particle azimuthal correlations. And in principle, the fact that the saturation scale, momentum scale, transverse momentum scale. So the fact of whether to what extent, how much does the saturation matter? How large is the saturation scale? That should be particularly well visible in when you measure these. These particles go into 2 particles that you measure, and then you look at okay, if it's really perturbed, that if there's no saturation, if there's no intrinsic transverse momentum, these are going to be exactly back to back. If you get no momentum from the transverse momentum from the gluon field, these are going to be exactly back to back. So the amount of transverse momentum that you get from here will influence the azimuthal angular correlations between these particles. They will be less and less back to back because they're getting more and more momentum from the target. So by comparing proton and nucleus, comparing this kind of 2 particle relationship, that has been considered a very promising signal to look for saturation. Unfortunately, of course, there are then other complications. But it's never ideally it's great. In practice, it's a little bit ambiguous, the status. I would say there's data from Rick, but everybody believes that I understand. So there's a lot of details in this. It's not as ambiguous as I think. It's not as clear as one would hope. So, but anyway, this kind of a thing is phenomenologically interesting in itself. I very much look at, but I think that's enough for today.
Thank you.
Okay,